Hi, and welcome to 8.3 Parametric Equations. Now, this section used to be the type of thing that, as a student, I was a little nervous about. I mean, the whole parameter parametric equation sounds kind of frightening, but it's really not. What we're going to do is we're going to have another variable, t or theta or something else, and we end up with two functions. X is a function of t or theta, and y is a function of the same variable. So we end up with two functions here. So let's go through this. So a parameter is a variable different from those representing the coordinates. Our coordinates are x and y, so another parameter, another variable comes up in this. X, y denotes a coordinate of a point, as we've seen before. If both x and y are considered functions of a third variable, say t, then t would be the parameter of x and y. We could say that x equals f of t and y equals g of t. So x is a function of t and y is a function of t. In this way, we could have both f of t and g of t be functions, yet together they can make the graph of a circle. Well, a circle is not going to be a function, except these two can be functions. So x equals f of t, y equals g of t would be called parametric equations because they're equations with a new parameter of t. That's all it's to it, just another parameter. So you maybe have a little more work because you have one extra equation to deal with. So let's take a look at example 1. Okay, given the parametric equations, x equals tangent theta over 2 and y equals cosine squared theta plus 3, identify the parameter and construct a table of the points x, y that will result from the values. Now, a parameter in this case is not t, it is theta. That's our parameter. So let's make a table here. And it says to go with 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. Then we're going to have our x equals tangent theta over 2. Should have said x of theta. And then y of theta is going to be cosine squared theta plus 3. So I made a table in my calculator for these values. Go ahead and get the decimals here. So if I put in 0 for tangent, 0 for theta on the tangent, I get 0. And 0 here, cosine squared of 0 is 1. 1 plus 3 is 4. Pi over 6, we're at 0.289 and 3.75. Pi over 3, we're at 0.866. And 3.25. For pi over 2, now tangent of pi over 2 is not defined, so it's undefined. And over here, cosine of pi over 2 is 0, so it's just 3. So notice how this is going down. For 2 pi over 3, we're at negative 0.866. And then for the cosine one, cosine cubed is going to be 3.25. And we're at negative 0.288, let's say 289. And really, we're going to round that off to 0.3 when we graph it. And then we have 3.75. And for pi, we're at 0 here, and at 4 for that one. So let's graph this. So I'm going to plot some points. So I'm going to go with 0.2, 0.4, 0.6, 0.8, 1, negative 0.2, negative 0.4, negative 0.6, negative 0.8, negative 1. 1, 2, 3, 4. 1, negative 2, negative 3, negative 4. Okay. So here are the ordered pairs, 0, 4. Change colors for this. Zero, 4. Then as theta gets bigger, we're at 2.89, 3.75. So right about here. And then we're at 0.866 and 3.25. And then we're looking at negative 0.866, 3.25. And then a negative 2.89, so basically negative 0.3, 3.75, and then 0, 4. So it's going this direction, and back that way. So if we kept on going, we see values going like that. Starting back here, going to there. And there's the graph of these parametric equations. Okay. Now the next thing we're going to do is talk about eliminating the parameter. So go ahead and feel free to pause here if you want to write this down. I'm going to move on. Eliminating the parameter is the process of converting from parametric form to rectangular form. So instead of having x and y be functions of t or theta, you can make it say y equals something with x. To do this, we solve one of the equations for the parameter and substitute the result for the parameter in the other equation. So we're going to sketch the graph of the parametric equation by eliminating the parameter. So we have x equals 1 plus t and y equals t minus 3 over 2. So let's solve for t here, subtracting 1 from both sides. X minus 1 equals t. Now we're going to substitute this result into t in the y part. Y equals x minus 1 minus 3 all over 2, or y equals x minus 4 all over 2, or y equals 1/2 x minus 2. Our intercept is negative 2. Our slope is 1/2, so up 1 over 2, or down 1 back 2. There you go. That is eliminating the parameter and then graphing the equation. And feel free to pause that. I'm going to scroll this up. So the next one we have x equals cosine theta and y equals sine theta. What would this one look like? Well, if we solve for theta, theta equals cosine inverse of x. And if we want to kind of go back thinking about this cosine theta, it means we have a right triangle. If this is theta, cosine of theta is x, so that's going to be the adjacent side over the hypotenuse, which means the other side is going to be 1 squared, which is 1, minus x squared, square root of that. So y will equal sine of theta. You could say y equals sine of cosine inverse of x. And so to get that, we can always just reference back to here. Because we're talking y is sine of theta, we can use this to evaluate that in terms of x. So if this is theta, sine is opposite over hypotenuse. So y equals the square root of 1 minus x squared. Now if I square both sides, I have y squared equals 1 minus x squared. If I add x squared to both sides, x squared plus y squared equals 1. That's the equation of a circle with radius 1. So if I call this 1, call this 1, call this 1, negative 1, and down here, negative 1, it's a circle with radius 1. Center at the origin. That's it. Now for the next one, this is actually kind of fun. We get to construct parametric equations described in the graphs of the following equations. So think of this as when we did composite functions back in pre-calculus. We got to break it up into two parts. So for example, in this case, a very simple one, you can say x equals t. I'm going to go a little more complicated. What if I said x plus 1 equals t, then x equals t minus 1, and then y equals t squared. That's kind of cool. So this part becomes t, so y is t squared, x is this part. X plus 1 is t, so x is t minus 1. Likewise, for the next one, we could say the x minus 1 equals t, which means x equals t plus 1, and y would be equal to the absolute value of t, because this gets replaced with t. That's what t is. Okay. Okay, the last problem here, I got to clear the board a little bit. Construct a parametric equation for the line with the given attributes. Slope is 1/2 and it goes through 10, 12. So we know our slope is 1/2, that's m. Here's x1, y1. So we'd say y minus y1 equals m times x minus x1. That's the point slope formula. So y minus 12 equals 1/4 times x minus 10. So y minus 12 equals 1/4 x minus 10/4. Then I'll add 12 to both sides. Y equals 1/4 x. That's minus 10/4 plus 12. So 10/4 would be, or 12 would be 48/4. So we get 38/4. So y equals 1/4 x plus 19/2. Now that's a standard equation, that's not parametric. You can make it parametric by just saying x equals t, so y equals 1/4 t plus 19/2. This is not the only way to do it, that's probably the easiest way to say x equals t there. We could have been more creative, but I think that works for our purposes. Okay, and that does it for section 8.3. Talk to you guys later.